All right, welcome back. So yesterday I gave you the crashiest of crash courses in Galois theory. It wasn't even really a crash course because I defined a bunch of terms. I told you what a Galois extension is. I gave you some different characterizations of the Galois extension, but I didn't give you the main show. I didn't tell you the fundamental theorem of Galois theory. Egregious. So we're going to correct that right now. The fundamental theorem of Galois theory, it is a really powerful tool because what it does is it gives you a way of understanding extensions of a field by way of understanding how the group of automorphisms that fix that field are acting. So the fundamental theorem of Galois theory states, I'm stating it only in the finite case, there is an infinite Galois theory and a corresponding fundamental theorem, but it involves a bit more effort to even define what an appropriate Galois extension is. And so we're just going to restrict ourselves to the easiest case, which is the finite extension case. So in the finite case, the fundamental theorem of Galois theory says that if I have a finite extension L over K, and it's Galois with Galois group that I'm denoting by G, then there is an inclusion reversing one-to-one correspondence between subgroups of G and subfields of L that contain K. This correspondence is given by, if I give you a subgroup H and I want to find the field that it corresponds to, I look for the subfield of L of all of the elements that are fixed by all of the elements of H. If I give you a subfield F and I want to find the corresponding subgroup, then I look for all of the things in G that fix the elements of F element-wise. Okay? This F is referred to as the fixed field of H. And this correspondence has some important properties. So the power of the fundamental theorem of Galois theory isn't just in the fact that we have this correspondence. It is in the fact that you can get important information about these field extensions based on the subgroup that it corresponds to. All right, so some important properties. If I give you two sub-extensions, F1 and F2, and I look at the subgroups, H1 and H2 that they correspond to, then F1 is a subfield of F2 if and only if. Here's where the inclusion reversing bit comes in. F1 is the smaller field of the two. It corresponds to the larger subgroup. Okay, so F1 is the smaller subfield, but H1 is the larger subgroup. One thing that the fundamental theorem of Galois theory, Galois correspondence gives us is if I want to know which subfields of L that contain K are Galois over K, so I'm looking for Fs that are Galois over K, what I really want to do on the group theory side is look for the normal subgroups of G. So, jumped ahead. There's one extension that is always guaranteed to be Galois over any subfield, and that is L itself. So L over F is Galois. And its Galois group is the subgroup fixed by F, or is the subgroup corresponding to F. And here's where we start to get even more information about the field extensions based on knowing things about the subgroups involved. So for one, this just comes from the previous fact that I wrote down. The degree of this extension is exactly the size of the Galois group of the extension because we're dealing with a Galois extension. That is the group H, and so this order of this degree matches this order. And if I want to know the degree of F over K, what I want to know is the index of H and G. But because we're dealing with finite groups, we have a nice formula for what the index of H and G is. Does anybody remember? Say it again. It's the order of G over the order of H. Okay, so if I want to find a subextension of a particular degree, what I'm looking for is a subgroup whose index is equal to that degree. So let me go over here. Don't forget the group photo. Also Cobb salad. This was the point that I started to say a bit earlier, but now we're going to say it here. If I want to know if a subextension F is Galois over K, what I really want to know is the corresponding subgroup a normal subgroup of G? So F is Galois over K if and only if the corresponding subgroup is normal. If this is true, then I can actually tell you what the Galois group is in terms of G and H things. So think fast, but don't overthink it. If I give you a group G and I give you a normal subgroup H and I want to get yet another group out of it, what might I do with G and the normal subgroup H? Quotient. And up to isomorphism, if I take that quotient, what I get is the Galois group of F over K. And I think this is the last one. Yes. Finally, if K, if I have these subfields F1 and F2, yesterday I asked you to consider something called the compositum. We can also consider the intersection of these two fields. And one natural question you might ask is if I give you a compositum or if I give you a subfield, meaning that I use some natural ways of taking these two fields to find other possibly different fields. What can I tell you about the Galois? The question that you might want to ask yourself is what can you say about the corresponding subgroups? So if I give you two subfields, and they correspond to subgroups H1 and H2. Then, if I look at the intersection of these fields, and if you've never proved to yourself before that this is also a field, you should. This is another subfield because each of these contains K. Their intersection contains K, so this is some subfield between K and L. By the Galois correspondence, it should correspond to some subgroup. The subgroup that it corresponds to is the smallest subgroup that contains both H1 and H2, and we denote that by this bracket, H1, H2. And if, on the other hand, I want a field that contains both F1 and F2, I can look at the smallest one that does. That's the compositum. This corresponds to the subgroup H1 intersect H2. We are interested in sketching out an argument for the Kronecker-Weber theorem, which means that we are focusing on abelian extensions, which means that not only do we have Galois extensions everywhere, we have some of the nicest groups we could hope for. We are dealing with finite abelian groups. We're about to use the fundamental theorem of Galois theory and the Galois correspondence and the fact that we're dealing with abelian groups to start squeezing the orange for all it's worth, right? So just so we can emphasize what's happening with the Galois correspondence and really just to highlight what we mean by this inclusion reversing thing and maybe how you might use this. Let's do a very simple example, but not too simple, of an abstract abelian extension, let's say over Q, and let's say that we just happen to know for reasons that its Galois group is cyclic of order 10. It's a relatively simple, straightforward group. Not so simple that it doesn't have any subgroups. I think that might be a pun or a joke about simple groups.
It's not tracking.
If you're looking back at this video and you're thinking, what did I miss? The fundamental theorem of Galois theory, you can find the statement all over the place. So go find a good reference that makes you happy, that has all of these properties. The keywords are Galois correspondence. Okay, so suppose L over Q is abelian, and just for reasons, we already know that the Galois group is cyclic of order 10. So here I'm declaring sigma to just be a generator. Okay. Let's think back to our group theory. Let's think about the subgroups of this abstract group of order 10 that I'm telling you is abelian. And let's see if we can figure out what the field diagram is going to look like. So what I want to do is I want to write down a lattice of subgroups. And then I want to look at that lattice of subgroups and ask myself, on the field theory side, what fields am I saying have to exist? Okay? So we're already starting with L. It's an extension of Q. We're going to fill out what are the subfields in between them. Okay? I'm going to write the subgroup diagram in what looks like an obnoxious way, but it's because I really want to use the fact that this is inclusion reversing, and sometimes my brain gets diagrams mixed up if I don't just sort of match them up in exactly the right way. I'm going to keep doing that. If you go to LMFDB and you start looking around and asking it for things like Galois groups or abstract groups, if you go to LMFDB beta, there is a little checkbox that you can click on an abstract group, and it's basically like, do you want to see the subgroup diagram, but do you want to see it in a Galois correspondence way? And it'll flip the diagram for you so that you can see what kinds of fields you should get if you have some abstract group, or if you have some field extension whose Galois group is isomorphic to that random group that you found in LMFDB beta. Okay. We're going to start with the two subgroups that we know are in every group. This one definitely, I'm saying in every group, but I just really mean two subgroups that I can always assert exist. I have this group, gal L over Q. I know it has to contain the identity group as a subgroup. What is the other group that I'm guaranteed to have? Don't overthink it. Itself. The whole group is a subgroup. What this is saying is the subgroup of the Galois group that fixes all of Q is the whole group. That feels almost tautological because that is how we define this. What this is saying is the only subgroup that fixes all of L is the identity. Good? Okay. What other subgroups do you know exist in this cyclic group of order 10? It's the subgroup generated by sigma squared. And what is the order and the index of that group? You should know both. The order is 5 and the index is 2. Since it is an order 5 group, I'm going to use this link to denote the order and this little link to denote the index. Good? Okay, so this is order 5, index 2. This is very suggestive. I'm kind of suggesting that we have another subgroup, because otherwise I could have just drawn a straight line. Yeah, sigma 5. So, order, index, Say it like you mean it. Index 5, yeah. All right. The correspondence tells us here, let's look for subfields starting with Q and working our way up. This is telling me that I have an index 5 subgroup. It has to correspond to some field extension. What do I know about the degree of that field extension? My hint is I didn't erase that yet. Yeah. I have some degree 5 extension. So degree 5. Question, is this extension Galois? Yeah, why? Exactly. That's one of the nice things we get by dealing with abelian extensions. Every field that we see in sight, every subfield of that abelian extension is going to be a normal extension and therefore Galois, because we're in the nicest case of perfect fields. I have another extension here. Is it Galois? Is L over F Galois? F1 Galois? Y'all are like whispering, you should say it with gusto. Yes. Yeah, it is. What is up to isomorphism? Do we know what its Galois group is? Yeah, it's isomorphic to the cyclic group of order 2. I'm missing a field extension. I'm just going to go ahead and fill in the rest. This is a degree 2 extension. Fantastic, it's quadratic. This is a degree 5 extension. Okay. Not too bad, right? Okay. So a thing that you might notice from this diagram, I told you that the Galois group was isomorphic to the cyclic group of order 10. So one of the things I'm telling you is that the degree of the extension is 10. And if you trace your way up from one field here straight up to the top, so you follow what we call a tower of field, you might notice that if I multiply the degree of this extension by the degree of this extension, I get the degree of the overall extension. That's not an accident, and it doesn't actually use the fact that this is Galois. That is just a feature of any tower of fields. So if I have a field, I have a tower of extensions, so I've got some K inside of some F inside of some L, and they're all finite degree. Then if I want to know the degree of the big extension, I can just multiply together the degrees of the 2 intermediate extensions. Okay. And we're probably going to use that throughout the rest of this lecture and certainly in the next one. Okay. Since we are interested in abelian extensions of Q, the Galois correspondence and the fact that we are dealing with finite abelian groups as Galois groups suggests one way that we can reduce the problem that we need to solve in order to prove the Kronecker-Weber theorem. Okay. Okay, so our extensions have finite abelian Galois groups. We're going to use that structure to simplify which extensions we actually need to prove are contained in cyclotomic fields. Okay, so the proof that I want to sketch out for you over the remaining lecture days is based on a proof that you can find in Ribbenbaum, and you can also find this as a series of exercises in Marcus's number field books. I will post links to both of those, or I will post the titles for both of those in the Zulip chat. Each of them is a Springer Link book, so if you have Springer Link access, you can get a free copy of each of them. For both of them, the method of proof is to first reduce the set of extensions that you are dealing with. So rather than considering arbitrary finite abelian extensions, we're going to simplify the set of extensions that we have to look at, but we're going to simplify several times. Okay, so our first step is going to be to not worry about an arbitrary finite abelian extension, but to only worry about abelian extensions where the degree of the extension is a prime power. So what we need to show is that it suffices to prove that any abelian extension L over K, where the degree is a prime power, sits inside of a cyclotomic extension. Okay. I'm saying that we need to prove this. This is the step that you all are going to prove. One of your exercises is outlining the approach that you should take. I'm going to give you an idea of what you're going to do. What you're going to do is you're going to say, this is a finite abelian group. I'm a mathematician. I have seen some group theory. I know how to break a finite abelian group up into prime power pieces. Once I've broken it up into prime power pieces, the Galois correspondence is suggesting, hey, what I really want to do is use that decomposition into some sort of breakup into prime power groups to pick out subgroups of prime power index, because those will allow me to find some finite degree extensions of Q that are a prime power index. And then you need to make an argument for why the correspondence is still giving you an abelian extension, this time one of prime power index. Okay? So this will be in the problem set. I have faith in you. You can do this. This really is, really truly, this is do a slight bit of thoughtful group theory and then invoke the Galois correspondence. That is what this exercise requires. So future you and a buddy are going to get together and you're going to do that exercise and you're going to say, fantastic, I did the first step in reducing the Kronecker-Weber theorem to a, in theory, simpler problem. All right. Any questions so far? Everyone in here has seen at least a little bit of number theory, and so I hope it's not surprising to you that a number theorist might make as one of their first steps. Make this into a prime power problem. Okay? And the fun part is all of our other reductions are just going to be, no, keep making more of a prime power problem. Okay, here what we're doing is we're making the degree of the extension a prime power, but there are other things that we also want to force to be prime powers. And what I'm going to do for the rest of the lecture is start to explain one of the things that we need to, I'm not going to define it, but we just need to understand what it does. And we're going to start sketching out an argument for why we can assume that this special number, this invariant called the discriminant of the number field, is also a prime power. That will again simplify what we need to look at, and then the hard work in the next couple of days is going to be, under those simplifying assumptions, do the rest of it. The rest of it is where the real work is. All right. So here when I say our remaining reductions, I mean our remaining ways of simplifying this problem or adding in additional hypotheses to reduce the set of field extensions that we need to actually prove the Kronecker-Weber statement for. And before I can state The next of them, I need to introduce the discriminant, but again, I'm not going to actually define it. I'm just going to tell you that it's a number, and a little bit later I will tell you what this number gives us, what information it tells us about the number field that we're dealing with, or at least some of the information. Okay. I'm going to use a lowercase delta to denote the discriminant of a field L. Here, in theory, in practice, you might want to define something like a discriminant for an arbitrary extension, so where you're not assuming that you're just dealing with Q as your bottom field, where maybe you have some other finite degree extension of Q, so maybe there's some field K, and you want to look at extensions of K. You can also define what's known as a relative discriminant, but here when I write this, I'm writing something that you can define no matter what the number field is. This is not just like a relative notion, it's an absolute notion. It's a number. It is an integer that we're going to associate to our field L. Okay. What you need to know about the discriminant at least to understand its role in this next result, is that, as I mentioned before, it's an integer. It tells us something about the behavior of primes. In the extension L over Q. And for any extension, not just a Galois extension, for any extension that is different from Q, the absolute value of this is strictly greater than 1. So there is exactly one field extension over Q for which the discriminant is either 1 or minus 1. In this case, it's 1, and that is Q itself. It might not look like it. This is saying something about what we call ramification. What this tells us is there are no non-trivial unramified extensions of Q. It's okay if you don't know what ramified and unramified mean. I'm going to wave my hands at what it means a little bit later. Okay. For this next statement, again, don't get bogged down in what the discriminant is. What you really need to know is, I am giving you an integer. I am telling you that that integer is 1 if the number field L, number field just means it's a finite degree extension of Q. If the number field L is Q itself, it is an integer whose absolute value is strictly greater than 1 in every other case. That means that it has a prime factorization, right? Up to a plus or minus sign. I can factor it into a product of primes, and we're about to use that. I'm going to state 2 results. The first of them we won't prove today, because even proving that, this next lemma is going to take defining some new and interesting things. But assuming that lemma, we can prove our next reduction step. All right. Assume L over Q is an abelian extension. And let's assume that its degree is n. If Q is a prime that doesn't divide n, then there is an abelian extension call this one F over Q. F is not, do not assume that it's a subfield. It is just another incidental extension. But it has a special property, a few special properties. Okay. The degree of this extension divides in L need not contain F, and it need not be contained in F, but it is contained in F adjoin. I'm going to call it epsilon, but it's going to still represent a root of unity. In this case, a qth root of unity. This prime Q that doesn't divide in, it also doesn't divide the discriminant, this case of F. Right, so our assumption is that Q, oh no. Ooh. Sorry, I am missing an important thing. Q is a prime, Q doesn't divide in, but, apologies, Q divides the discriminant of L. All right, so Q divides in, Q, what am I doing? Oh, bother. Put a pin in this. I think I'm making a mistake here. I may need to come back and correct this. I do need this assumption. I'm assuming that I have a discriminant that's not a pth power. That's really how I'm going to use this a little bit later. My apologies. If need be, I will correct this in the notes that I post later. Okay, so Q is a prime. It doesn't divide. Nope, doing it wrong. Exactly wrong. Okay, Q is a prime dividing the discriminant. That's the condition I need. Let's try it again. I want to reduce to the case, I want to eventually reduce to the case where I can assume that the discriminant of L is a prime power. If it's not a prime power, then if it's a prime power extension, but it's the discriminant is not a prime power, what I want to do is I want to remove any extraneous primes. And so I'm going to start by assuming that I have a prime that divides the discriminant, but doesn't divide the power of the extension. So if this is a p power extension, here I'm saying that Q is something different than p. I want to make an argument for how I get rid of this extra Q. And so what I'm going to do is I'm going to find an abelian extension, F over Q, where the degree of F still divides in. L is contained in this cyclotomic extension of F. And I have gotten rid of this extra factor from the discriminant of L. So the discriminant of F no longer includes this factor of Q, but if Q prime is any other prime that does divide the discriminant of F, it also divides the discriminant of L. Okay. Yes? I'm saying Q does not divide in. All right. Again, let me tell you how this is going to be used so that you understand why we care about this. I want to reduce the cases of the Kronecker-Weber theorem that we need to consider to just the cases where the degree of the extension is a prime power p. That is what your exercise is about. That's the work that you're going to do. But I also want to reduce to a case where this mysterious invariant that I haven't told you much about is also a prime power. It's a power of the same prime p. Yes?
It's not necessarily a sub-extension of L?
No. It is just some extension that I know exists and is abelian. Okay. So I want to reduce to the case where L has prime power degree, and for that same prime power, its discriminant is also a prime power p. is also a prime power, right? So if the degree of the extension is p to the m, I want to be able to argue that the discriminant is p to the s. But the discriminant, all you know about it right now is it is some integer. It's some integer whose absolute value is strictly greater than 1 in the cases that we're considering, which means that it has some prime power factorization. If I have some primes q other than just the p that I want to focus on in the expression of, or in the factorization of the discriminant of L, I want to make an argument that allows me to get rid of that by constructing another extension where I no longer have this extra q, but I am giving myself a field that is starting to look vaguely cyclotomic. Okay, so this is not a cyclotomic extension necessarily, but this epsilon, it is a root of unity. And so this is looking at least a little bit more cyclotomic than it did before. Okay? All good? Okay. All right, I think I recovered. We're going to keep going. Assuming this lemma, we're going to do our next reduction step. So theorem, if it suffices to prove the Kronecker-Weber result, for the Abelian extensions, bless you, that have degree of prime power and discriminant of prime power. Okay, in other words, we don't have to prove Kronecker-Weber for an arbitrary extension of prime power degree. We can instead focus on the case where we are dealing with extensions where we know that the degree of the extension is a prime power, but also this important invariant, the discriminant, is a prime power with the same prime. And if you're wondering, does this ever happen? Yeah, actually, this happens for like the, nope, I was about to tell a lie. Not gonna tell the lie. It does happen, but I will point to it a little bit later. It's a bit more complicated than I was about to say. Okay. All right. Let's do our proof. So assume L over K is an Abelian extension of degree p to the m, where p is prime. Okay. If the discriminant of L is already a pth power, we're done. So assume that you have a prime distinct from p dividing the discriminant. So suppose there is some q, let's call it q1, different than p, dividing the discriminant of L. Then by the lemma, there is an Abelian extension. Let's call it F1 over Q, and a root of unity, let's call it epsilon 1 such that the degree of F1 over Q, the theorem says that it is a number, so the degree is a number that divides n, but n is already a prime power in this case, right? That's what this assumption is about. So we're assuming that the degree of the extension is a prime power. That means that the degree here has to be another prime power for the same prime p. And if, let's see, what am I calling it? If Q prime is any other prime dividing the discriminant of F1 then Q prime divides the discriminant of F. Okay. What do we gain by this? What we gain is delta F, the discriminant of F1, so delta F1, has strictly fewer prime factors than delta L. Is everyone on board with that? Okay, so I started with some integer. I have just given myself another integer whose prime factors are a subset of the prime factors of here, but I know that I have one less, at least one less. I'm about to say the words, rerun the argument with F1 if it has a prime divisor other than P. Can you think about where we might be going with that? So I'm giving you an integer. I have just removed one prime factor of that integer. And I'm about to rerun an argument that allows me to remove prime factors. What do you think is going to happen?
You're going to keep removing them until you get one.
Yeah, integers only have so many prime factors. If I just start picking them out one by one, eventually I run out of prime factors. That's where this argument is going. So if F1 has some other prime factor in its discriminant, just rerun the argument. And the point is, we're dealing with integers, we're removing prime factors. Eventually, the thing that we're doing has to terminate. I have to stop after finitely many steps. Okay. So if delta F1 is not a power of P, rerun the lemma to get an F2, an epsilon 2, and a delta F sub 2 with F1 contained in F2 adjoint epsilon 2 and delta F2 having strictly fewer prime factors than delta F1. This process has to terminate. After finitely many steps. Let's say that we took our steps to do this. And then let's see what we've got. So in our last step, we have an extension, FR, whose discriminant, delta FR, is a power of P. We are allowing for the possibility that FR is actually Q, so maybe you just removed all of the prime factors and you got down to the rational numbers. So its discriminant is a power of P. Its degree over Q is also a power of P. And sort of running this one more time if we need to. We conclude that FR is contained in Q adjoin some root of unity. Okay. I'm not making any claims about which root of unity it is. I'm just saying that I have run this argument enough times so that I've gotten myself down to a prime power extension that is contained in some cyclotomic extension. Okay? But I said earlier that I didn't make a claim that F was contained in L or L was contained in F for any of the FIs. And so we do still have something to do. We need to explain why this gives us that L is itself contained in a cyclotomic extension. And so here's the final step. What we have are these containments. L is contained in F1 adjoin a root of unity. F2 is contained, or F1 is contained in F2 adjoin a root of unity. And we've just kept going so that I have some field F sub r minus 1 contained in FR adjoin a root of unity. Oops, wrong index. And finally, FR is contained in an honest to goodness cyclotomic extension. But this means that I took something in a cyclotomic extension, adjoined another root of unity, and then if I do one step back, adjoin another root of unity, adjoin another root of unity, and just keep adjoining all of the roots of unity that I encountered along the way. And the conclusion is, peel it all the way back. This is contained in an extension where I adjoined a bunch of roots of unity, and my claim / your exercise to finish this off. I claim that this is contained in some cyclotomic extension. Okay? All right. We mostly did it. You've got like a little box. Normally I fill in the box if I've completed a proof. This one is like a half filled in box because there's an exercise that you all need to show. Oops, I'm telling a lie, telling a lie. Not necessarily equal to, just asking you to show that it's contained in some cyclotomic extension. Okay. All right, everyone like stretch out, take a breath. Just did a lot of writing. I threw a lot of random field extensions at you. But this is the next key step in our reduction. And before we finish justifying that reduction and then pivoting to the remaining cases, because once we're done with this, what this means is we just focus on the cases where we have an abelian extension of degree p to the m and discriminant p to the s up to a sign. And then, again, your number theorists, you will be unsurprised to realize that we need to separate out the cases where we have odd prime powers and powers of 2. Okay. You're so early in your mathematical journey. You've probably noticed that 2 will sometimes give you trouble. 2 is just going to keep giving you trouble for the rest of your mathematical life. Make peace with it. 2 is fun and weird and strange things happen. Okay. So we use this quantity delta L in the last lemma and theorem. And it is an important thing. It is important, especially when you start learning algebraic number theory, to understand how the discriminant can be computed. I'm not going to do that. Instead, I'm going to tell you some important facts about the discriminant. I've already told you one of them. One of them is it is an integer. And I've hinted at one of the reasons we care about the discriminant, and it's because it is telling us something about how primes behave in extensions. But even then, I was playing a little bit fast and loose because I just said prime, and you probably in your heart said, she just means a rational prime number, and you probably just perked up and thought, what does she mean by a rational prime number? What other kind of prime is there? Every prime is a rational number. Yes, but also no. Okay, we're going to start talking about things called prime ideals. If you haven't seen ideals before, if you are unfamiliar with ring theory, that's okay. I'm going to give you the bit of information that you need in a series of exercises for you to understand why some of the things that I'm going to say about these strange objects that you might not have seen before called ideals are true. Okay. So before explaining one of the things delta L does, we're going to revisit some things that we know about the integers. And I promise we're going somewhere with this. Okay. I'm going to give you a list of properties of the integers. 1, it's a subring of Z. It's a Tuesday. It's a subring of Q. Okay. 2, its field of fractions is Q, and we denote this by FF for field of fractions of Z is Q. 3, you may have heard of something called Gauss's lemma. If I give you a polynomial with integer coefficients, and if I give you some rational number that's the root of that polynomial, then B wasn't just any old rational number, it was an integer to begin with. This property means that Z is what we call integrally closed in its field of fractions. The 4th property is that the integers is the smallest subring of Q for which 2 and 3 are true. There are other subrings of Q that have those properties, but all of them contain the integers. So it's the smallest here based on containment. And here I should say, when I say subring, I always mean a ring with identity. For those of you for whom that means something. fifth. Every non-zero integer can be factored uniquely. It's the fundamental theorem of arithmetic. And sixth, if P is a prime, then the quotient ring Z mod PZ is a field. Yes?
For number 3, we want F to be monic, right?
Yes, thank you. Thank you so much. Ooh, ooh, good catch. Brownie points to you. Yes, that is very important. Otherwise, I just told a big old fib. It's too big to just be a fib. I told a lie. Capital L lie. You need monic. Okay. Never enough time. What we want to do is we want to find, given an extension, a finite extension L over Q, we want to find a subring of that extension that has as many of these properties as we can manage. Okay? We want something that's a subring. We want its field of fractions to be whatever our extension L is. This is actually the most important thing, at least as a starting point. We want it to satisfy Gauss's lemma within its field of fractions. We want it to be the smallest subring of L that accomplishes 2 and 3. Such an object exists. We call that object the ring of integers of L. I'm going to tell you how it's defined. I think I'm running short on time, so I may just have to put this in the notes online. I will tell you out loud how it's defined, and then we're going to run into problems with this one. Okay? The ring of integers of a field L over Q, L is finite, is just all of the things in L that are roots of a monic polynomial with integer coefficients. You have things other than just Z sitting inside of such a subring. Okay? There are examples of such rings for which unique factorization of elements doesn't hold. But we recover as much of this as we can by saying, I can't do it with non-zero elements, but I have another object, another kind of object called an ideal, for which I can get something like unique factorization. And then, under that unique factorization, there are things that take the places of prime numbers. They are called prime ideals. Very inventive language. Those prime ideals also have the property that if I look at the quotient of my ring by that prime ideal, I also get a field. Okay. Alvaro, are we out of time?
I think so.
Okay. Since we're out of time, we will pick back up with the ring of integers tomorrow. No, in the notes today, because you have exercises involving the ring of integers. All right, and I will take any questions that you have.